Hi everyone, thank you for taking the time to come to my presentation today. My name is Alex Kitchell, and I am a chemist with Biosynthetic Technologies. Just a little bit of a background about me. I got my undergrad from Hanover College and graduated in May of 2018. I am now pursuing my MBA at Ball State University in addition to working at Biosynthetic Technologies. Today in this presentation, we will be talking about comparing the hydraulic stability of base fluids. So a quick overview for this presentation today. We will first look at the background and terminology that is commonly associated with EFFs, or environmentally friendly fluids. We will then move in to environmentally friendly fluid requirements in EALs. After that, we will look at what is hydraulic stability. We will then move in to hydraulic stability testing and results that you might typically see and what they look like. Lastly, we will look at the importance of hydraulic stability and its importance for EFFs. So historically, as is now well documented and well known, petro-derived products are not sustainable, nor are they eco-friendly. These products can contaminate the environment and cause severe environmental harm, especially in the form of oil spills. Oil spills most commonly are known for occurring in the water, but there are a lot of problems associated with oil spills on land too. So now a new era is arriving and has arrived where we have to use and want to use EFFs or environmentally friendly fluids. Now scientists, formulators, governments, environmentalists, chemists, and lots of other people are searching for these eco-friendly products that will replace their petroleum-derived products. These eco-friendly products are often now known as EALs, or environmentally accepted lubricants. While these EALs reduce environmental impacts, it is also a cause for concern that they come with many performance disadvantages that their petroleum-derived product counterparts do not have. One of these huge disadvantages is hydrolytic stability. So why should we use EALs? EALs can be any combination of these or any one of these. But first, they can be biodegradable. They can also help cause a decreased dependence on the petroleum-derived products. From this, you will also see reduced carbon and greenhouse gas emissions. The products can be renewable and recyclable. It can also help improve the LCAs of various companies and organizations, which are life cycle assessments. These are becoming increasingly important when it comes to sustainability, and they can help. A good LCA, such as carbon negative or carbon neutral, is very important to most companies. They can also be non-toxic, bio-based, and have low bioaccumulation. And we know that today regulations are forcing companies to focus more on environmentally friendly fluids. So it's important to get ahead of the curve and start using EALs. So what do these terms mean? Well, renewable just means that it is a product that is made from plants or other regenerating material, and that it can be restored to its original state. Recyclable just means that it can be returned to its original state. And bio-based means that it is derived from renewable resources, which generally include plant-based products. Biodegradable, a term most people are familiar with, means it is able to be decomposed by bacteria or other living organisms. These fluids have to meet standards for biodegradability, but it can be from any source, which is important. They are also non-toxic, which means they are not toxic to wildlife, and then bioaccumulative is the contaminant concentrations that build up inside wildlife when they are consumed. So EALs are environmentally accepted lubricants were pushed hard by the US VGP or Vessel General Permit. This states that the lubricants needed for all oil-to-sea interfaces after December 19, 2013 must exhibit three characteristics. One is that they must be biodegradable. Two is that they must have low toxicity to aquatic organisms. And then three, that it has a low potential for bioaccumulation. So government regulations, or EALs. Governments are looking for ways to regulate these EALs that could potentially harm the environment. For these EALs, they are divided up into 4 groups. So first you have hydraulic environmental triglycerides, or HETGs. These are also known as vegetable oils. You then have hydraulic environmental polyalkylene glycols, or HEPGs. Third are hydraulic environmental synthetic esters, or HEES. And then lastly, you have hydraulic environmental PAOs and related products. Undefined is usually considered STLEs and then eco-hydrocarbons or renewable hydrocarbons. For the sake of this, STLEs essentially are a subset of synthetic esters and would probably most closely belong in the HEES category. So the two that I am most focused about and going to refer to are the conventional vegetable fluids, or the HETGs, the triglycerides, in the synthetic esters. They both have a similar oxidative instability result, which is a weakness for them. When it comes to oxidative stability, they are more susceptible to oxidation when higher temperatures do occur. This can lead to shorter drain intervals, and meaning that these need to be changed out more frequently than other EALs. They also have a hydrolytic stability weakness, which means they are more prone to hydrolysis in the presence of water. Similarly, they are also both compatible with most seals and metals. However, the HETGs tend to have excellent frictional characteristics as well as viscosity index, while the synthetic esters, because they are synthetic, tend to be more expensive. You also have the HEPGs, which are fire resistant and have good hydrolytic stability. However, they do have compatibility problems, and they do tend to absorb water, which creates a rust and acid. Meanwhile, the PAOs have excellent frictional and anti-wear performance. They have similar durability when it comes to mineral and synthetic oils, and a good hydrolytic stability. They also tend to have a longer fluid life, meaning shorter drain intervals, good demulsibility characteristics, meaning they separate from water, good seal compatibility, and a broad temperature range. So if you were to compare these, you would say that HEPGs are the most equivalent to the mineral oils. You then have the HEPRs, which tend to have good hydrolytic stability. It's the HETGs and the HES that tend to have poor oxidative stability. If you break this down into base oils, you will see that Group 2, Group 3, renewable hydrocarbons, PAOs, and PAGs are typically excellent or very good when it comes to hydrolytic stability. It is the esters that perform very poorly. The exception to this is STLEs, which tend to perform very well. So I keep mentioning hydrolytic stability, but what is it? Well, for most lubricants and oils in general, water is a very destructive element. So hydrolytic stability is how stable it is in the presence of water, and is also the ability of a fluid to resist this hydrolysis from occurring. As we know, oils are innately and inherently hygroscopic, meaning they will absorb water and moisture from the air. In order to determine how fast this will occur, tests can be run to determine how much and how fast. There are additives that can help and hurt, but they are not things like anti-foam or antioxidant where they are derived specifically for that cause. Anyways, additives with high TAN can cause more rapid hydrolysis, which leads to a faster breakdown, where additives such as epoxides and carboimides can act as acid catchers and reduce hydrolytic stability. However, more research needs to be done to look at the characteristics on other properties, such as oxidation and anti-wear, which it could potentially hurt. So what are the effects of hydrolysis on oils? Well, first, you usually will see the formation of acids, usually in carboxylic form. This will then lead to rust and corrosion and valve sticking. You will also see degradation of the oil. This includes viscometric changes, including a loss of viscosity index, or VI, and equipment performance issues. You will also see increased seal swelling, which can lead to leak spills and poor machine performance. And then finally, you can also see a decreased load carrying capacity of the oil. So how do we measure hydrolytic stability? We use the ASTM method D2619. This method evaluates 4 to 5 different areas, which the main 4 are the weight change of copper, the appearance of the copper itself, which is another ASTM method, ASTM D130. You will also look at the change in tan of both the oil layer and the water layer. The change in tan of the water layer can also be called total acidity of the water layer. And then if you want, most companies can also report the change in viscosity. So how does water even enter the system? This can be done through a variety of ways. The first is thermal breathing. So when a system kind of oscillates between warm and cool temperatures, it can cause any kind of swelling, seal swelling. It can, and various other problems that water can leak in. You can also see both a high pressure blast or indirect water spray, which incidentally causes water to enter the system. You'll occasionally see a gravity draining of the condensate, and then there are just a bunch of various other ways that are still possible and you may not even know are occurring. So what is ASTM D2619? How does it work? Well, this method, known as the hydrolytic stability of hydraulic fluids, also known as the beverage bottle method, is run at 93 degrees Celsius. What you do is you add 75 grams of your lubricant or oil and then 25 grams of distilled water and then add a copper strip, and you will seal this into a literal Coke bottle. These are then rotated at 5 RPM for 48 hours. Afterwards, the layers are separated and go through treatment, and a full analysis is performed. An example of hydrolytic stability results. Before I start, it should be noted that this top is modified from 48 hours to 144 to better see longer term impacts of the hydrolytic stability. On the top, you can see an STLE is used, the high vis one, as well as a PAO, 2 various PAOs, and then a paraffinic bright stock and a naphthenic bright stock. Of the things that are most commonly recorded is the total acidity of the water layer that is most commonly reported. Below on the graph, you will see the Parker-Dennison limit for 2 different areas, the copper weight loss and the tan increase in the water layer. For the copper weight loss, it is usually a 0.2 max, whereas the change in the water layer, the tan increase, would be a 4.0. So here is a typical base oil comparison that you might see with hydrolytic stability using the ASTM D2619 method. On this, we have 3 different STLEs, a low vis, a medium vis, and a high viscosity grade. We also have a low vis and medium vis polyalkylene glycol, or PAG, as well as polyalpha oleifin, PAOs. There's also a low vis group 3 and 2 different esters, a C8 pentaerythritol ester and a complex ester. As you can tell or recall that there are 4 different primary measurements recorded in this test, and all 4 are recorded here. Of the 4 is the total acidity of the water layer that is most commonly talked about. In this case, you can see that the total acidity of the water layer of the STLEs did pretty well, even surpassing the excellent PAGs. One of the PAGs, the low vis PAG. There is also the esters, on the other hand, which were very acidic and even formed emulsions. The appearance of the copper panel, the C8 pentaerythritol, as well as the high change in total acid number tan, continues to show how poor hydrolytically stable most esters actually are. It's also a hydrolytic stability torture test, which is something developed by biosynthetic technologies. This test is based on a more realistic and long-term scenario. So what happened is the lubricant was measured into a vial and added with 1% DI water. The temperature was set to 180 degree F, and the test was run for 12 weeks or around 3 months. The stir rate was about 500 RPMs, and it should be noted that these were in sealed containers where only the tan layer was measured for simplicity reasons. The water was removed. The purpose, again, was to understand long-term hydraulic stability effects. What happens when it's exposed to water and heat? How does this affect the change in tan over time? And we wanted to look at how it affected several different types of base oils. So the results of this test are very interesting. You will see that, again, the low-vis and high-vis PAGs, the PAOs, and the group 3 all tend to have excellent hydraulic stability. You will then see that the STLEs, or the top 3, tend to have good hydraulic stability and can last for a much longer time than their ester counterparts, which are at the bottom. The ester counterparts, the complex ester, a C8, pentaC8 ester, a diester, and a TMP ester, all had a very fast breakdown. These products were extremely prone to hydrolysis, as you can see from their tans. On the next slide, we can look at graphs. So if you look at the graphs, the first one on the left shows how unstable hydrolytically the esters actually are relative to everything else that was tested. If you move over to the right graph, you can see it closer up, and you can actually begin to compare the STLEs relative to the PAOs, PAGs in group 3. While we know that the PAOs, PAGs in group 3s tend to have excellent hydrolytic stability, the STLEs are right there. It is the other esters that are not hydrolytically stable. So how do we prevent hydrolytic breakdown and increase the hydrolytic stability of our products? The way to prevent this or substantially slow hydrolysis is to employ bio-based base oils that have the following criteria. The first would be a starting total acid number, or TAN, that must be low. We know that as the TAN is higher, it leads to even faster breakdown, meaning hydrolysis will occur even quicker. A low TAN will ensure that the product lasts longer. You would also want a product that has a high degree of molecular complexity and also provides exceptional steric hindrance benefits. We also know that oxidative stability and hydrolytic stability tend to go hand in hand. Something that is oxidatively stable tends to be hydrolytically stable. So if you want to increase the hydrolytic stability, you want to find a product or find an additive that is also oxidatively stable. Lastly, having great emulsibility characteristics is important. This ASTM method is D1401, and it separates the water from the lubricant or oil after mixing. When the products separate like that, it suggests that they will not mix as well. Thus, the breakdown in hydrolysis will not occur as quickly. And lastly, if we're looking at the importance of good hydrolytic stability, first is that it causes less molecular breakdown of the lubricant. This will ensure a longer performance at a higher quality. This can also particularly help in areas where there is a high chance of water contamination. So areas like marine applications, various outdoor applications, and hydraulic systems will also be extremely benefited from good hydraulic stability. And lastly, hydraulic stability helps prevent rust and corrosion issues. This prevents and limits damage to systems, which can cause system malfunctions and various other problems. Overall, hydraulic stability is incredibly important and is something that everyone must consider when looking at the use of EFFs and EALs. And with that, my presentation has concluded. So I'd like to give a big shout out to the BT team for all their help and insight. In addition, my contact information can be found right here. It is simply akitchell@biosynthetic.com. At this time, I would like to thank you all for coming to my presentation. and I'd be willing to take any questions that you might have.